This video is for section 7.5, Roots and Zeros. We start off with the fundamental theorem of algebra, or FTOA, and it starts out with the basic premise that you have at least one zero. So you have the existence of a solution, and then specifically it has n zeros, including multiplicity. So n would be for the degree of the polynomial, like we see down below in the first example. The degree is 3, and so we should expect to see 3 answers in the end. Sometimes, however, the answers are repeated. So if we just kind of think about a simple polynomial equation, x cubed equals 0, and by inspection solve that x equals 0, that's actually a root that occurs 3 times. We'll cover this idea of multiplicity more in depth later. Moving on to the first example, we will solve by factoring by grouping. So we split the problem into 2 halves. We take the GCF of the first half and of the second half, noting that the negative comes along with the GCF because the first term in that group has a negative. From here, we factor out the GCF for each half. If we did not get the same 2 binomial factors, this problem would not be solvable by factoring and we'd have to use graphical techniques. But we did find a common binomial GCF, so we'll now factor them out front as a single copy, and then their cofactors form a group of their own. Usually I would solve the blue factor using the square root property, but to set us up for later in this lesson, I'll continue to factor this all the way down so that we realize a difference of squares. Factoring technique applies. And so we could set each of these factors equal to 0 using the zero product property, and then solving each of these equations by changing the sign, since they're only one-step equations, linear. And so really we have this list. Now we could also change our perspective here and say if we start with the answers, we would be able to work from them step by step by step to get all the way back to the original. And that's what we're going to do in the next section. Let's have a preview first. Notice you're given a list of answers known as roots, and the first thing to do is set them equal to x, because that's what they are. They're the x values that make the equation true. Then we want to set them equal to 0, because if they're individually equal to 0, then their product equals 0 by the zero product property. And that allows us to string these 3 individual parts together into one whole, which we can then distribute through, and then distribute through, and generate the original polynomial. So the shortcut then is to go from the list of numbers to their opposite sign and thrown in with an x in parentheses. For the first example down below, I'll go through step by step. So here we have writing polynomial functions. Please note that we have 2 theorems, the irrational and complex conjugate root theorems. This comes from the quadratic formula. So whenever you take in the quadratic formula the positive and negative square root means that anything with the square root is always going to come in a pair, both in a positive and a negative case, hence the word conjugate. please understand that if the radicand here is positive, then you get two rational roots. Like with the first example, we'd have to put in here -2 square root of 3 to have the complete list of answers. Noting that I'm providing only the limited amount of information possible to indicate that there is going to be a degree of 3 polynomial. Similarly, again from the quadratic formula, if the discriminant is negative, then you're taking the square root of a negative, then we get an I, like here in the second example. But notice it also comes in a positive and negative pair, known as a conjugate pair. And so for the second example, before we even begin, we'll need to bring to the table the -3i. So if it's positive, then it goes negative, or vice versa. Going into the first example, showing all of the steps, we first set each of these equal to x. I'm going to write all the steps in blue that we will later skip over once we identify the shortcut. You now set each of these equal to 0, so you change the sign in order to move the constant to the other side. Now that each of these equations are equal to 0, I can now set their product equal to 0, and I'm going to change the color because this could be your first step, realizing that you always just change the sign of the number in a parenthesis with x. But for the next part, I'm going to show in blue because I'm going to take this conjugate pair, an irrational conjugate pair, and I'm going to FOIL with them. But notice because of the opposite signs, just like when we rationalize, say, a problem like this, we always use the conjugate pair because the inner and outer products subtracted out to 0. This will result in the following. So notice I did not do the inner and outer products of that FOIL. But just to show all the steps, I will in this problem. And what that means is I'm going to let the x plus 1 hang out because it doesn't have the conjugate pair. So if I were to start the foiling, say, with these terms, then things will get awfully messy very quickly and the problem becomes 4 times harder. Instead, here in blue, I'm going to show all the work. I'm going to do FOIL first term, second term, and now I'm going to do the second distribution. -2 times 2 is -4. Square root of 3 times square root of 3 is square root of 9. When square rooted is just 3. Now notice, as advertised, the inner and outer products subtract out to 0. So from this point forward, we won't do those products of foiling. So I clean up a little bit, combining like terms, multiplying, and now we straight up FOIL. Or do distribution twice. It's not in descending order, so I rearrange for standard form in order to have our answer in its proper format. So in the next example, we're going to proceed similarly, except we're going to skip all of the blue steps. So right away, in the next example, I'm going to change the sign of whatever number I have, put it with an x in parentheses. And set their product equal to 0. So now we have two pairs that look like differences of squares. Here on the right we have a pair of complex conjugates. So I will multiply them together because then the distribution is easier because I could skip the outer and inner product. Now, negative 3 times positive 3 is negative 9. I times I is I squared, which is equal to negative 1. So that is multiplied by that 9, making it positive. And then I'm going to FOIL. X squared times x squared is x to the 4th. And now, because with FOILing, we always ask, what is the pair of factors of the constant that sum to the middle term? So in reverse, I could simply say negative 4 plus 9 is positive 5, x squared. So let me explain that now that I have that on the screen. The factors of negative 36 that sum to positive 5 are negative 4 and 9. So in reverse, the sum of these constants is always the middle term's coefficient. And that works as long as these first terms in the binomial factors are the same. And I'll box that answer as a possible polynomial that gave us these 4 roots. And notice by FTOA, the fundamental theorem of algebra, the degree is 4, and we did have 4 answers. So I'm going to clear the screen, working out this problem at the bottom. Remember, it is the term with the I or the square root that you have to negate. So the 1, the real number part, stays the same, and then it's plus 4i. And that all comes from the quadratic formula, the plus or minus the square root part. So we go ahead, you set each of these equal to x, and then you subtract them over. So really what you get is the following. So you get x minus this quantity. Because it's more than one term, I have to use parentheses. So it looks pretty complicated, but the concept is still the same. You always take the opposite sign of the root that you are given. So ideally in the future, really you just take the opposite signs of these whole factors. So then you distribute through the negative. Let's see what we get. And notice we've developed a new shortcut. Is that, like I said, as long as you just distribute through the negative for each of these, the real number part will always be the same because it always starts the same. But then it is the imaginary part that goes in as opposite. That will always happen. From here, I'll show all the steps, but anything with an I to the first power will subtract out to 0 because, again, we have the opposite signs with the terms including the I. So I will distribute. And anything that's going to subtract out later, I'll write in blue. So in the future we know that we don't have to write it. Now I'll do the next distribution. And the last distribution, distributing through the 4i. Now, the very last term, I have to multiply the 4i times the negative 4i. Negative times negative is a negative. 4 times 4 is 16. And I times I is I squared, which is negative 1, so then that goes positive. Please note that everything in blue has a pair. So this goes with this, and these pair off, and they all subtract out to 0 as advertised. So whenever you're going through the distributions, so distributing this to here, then to there, make sure whenever you hear yourself produce a product that just has an I to the first power, don't even write it down. Skip over it. So let's clean up what we have. Now we got a negative x and a negative x for negative 2x, and a plus 1 there. And then we have a plus 16. So that'll be plus 17. And that is our polynomial. Notice it has a degree of 2, and we had 2 roots. In this case, both were complex. So the shortcut here, in order to get these terms right away from this, it's basically you take the x minus 1 as a quantity squared, and then you add to it the product of the 4i squared. So let's take a look how that works out. Sorry, you take the subtraction of it. So we take a look, and we get this as a binomial squared, the first term, double their product, and then you square the second term. And this turns out to be the opposite of 16i squared, which then makes that go positive once we simplify away the I squared. And then notice how that gets us to our answer. That shortcut may not be worth remembering because it's a little more involved, but I think being able to go right to this step here is really important, where you just take the negative through rather than setting up these brackets. Let's take a look at the last page. So here we will need the free GraphCalc app on the iPad because I am not providing you with any of the possible factors. So what we do is we take this and we put it into the free GraphCalc app. Let me show you that. So first you go through and open up the free GraphCalc app, and you'll see a tab at the bottom for y equals sine x equations. So you tap that, and I believe it will open you up to this screen. And then if you have anything here, you just hit like clear and save. But you go ahead and tap on this section if you want to use red, here if you want to use blue. You go ahead and input your equation. Here's your variable x. Here's your caret for the exponent. And then you go ahead and hit save in the lower right hand corner. Then you will hit the third tab at the bottom for graph. Make sure to squeeze your axes vertically and horizontally in order to adjust the window and your scale so that you can see your intercepts clearly. Both of them are integers in this case. And now we will use -1 as an x equals and a 4 x equals. And we will use those in synthetic division to divide out 2 copies of x from x to the 4th, so we'll get down to something that's quadratic, and then we'll be able to solve from there using our quadratic techniques, factoring, square root property, etc. So going back to the notes, here are the steps. So you find the x-intercepts on the free GraphCalc app. Now I'm going to synthetically divide them out and then solve using quadratic techniques. So we said on the calculator the x-intercepts were -1 and 4. So it doesn't matter the order. I think -1 is easy to multiply with. Grab the coefficients. All powers are present, so I don't need to use 0 as a placeholder. Leave a little space, block off the remainder, and then you add down, adding to nothing, multiplying down and across, putting the product underneath the next coefficient, and then repeat the process. Add down, multiply down and across, and continue. Notice we get a remainder of 0. That's expected because we already said that this was a factor or a 0 of this function. So now we need to chain our synthetic divisions. This is a very neat application of synthetic division. Instead of rewriting this whole thing and then as the coefficients like we did here, we could just pick up where we left off by now taking this 4 as our half box number here and then making our synthetic division bar one shorter. So notice we don't include this part because that's the remainder. And then we repeat the process. So add down, multiply down and across. Sorry, that was a typo from before. That's a negative 36, and then we multiply to a positive. So now I have a positive 36, and that goes to 0. Now, we are using synthetic division to break down the polynomial so that the degree is smaller and allows us to use a lot of quadratic techniques to solve, noting that this is the remainder, the constant x, and now it is down to x squared. So we put the coefficients back with the variables. We set this equal to 0, and we could solve using quadratic techniques. Here I will use the square root property, setting it equal to 0, and taking the positive and negative square root of a negative gives us 3i. So those two answers with these two answers, which came from here and here, give us the 4 terms that give us the fundamental theorem of algebra. The fully factored form, remember you always put it with x, but you go opposite. So I could rewrite this whole polynomial as x plus 1, x minus 4, x minus 3i, x plus 3i, all equal to 0. And that would be the fully factored form of that polynomial. Going to the last example, again, we will put this into the free GraphCalc app. So I went ahead and I put in this equation. Notice it's written up here. And I adjusted my window under the graph tab so I could squeeze and see what this really is. And notice there's cubic. That kind of makes sense. If you double tap the screen, you'll get these options. Let's say this wasn't an integer value, and let's say it was like 0.3 repeating or 1/3. Then I could go ahead after double tapping the screen to bring up this option window. I could say find roots, and then I could drag this, a dot will appear on the screen, and I could drag it over left or right until it like locks in on that value, and then it'll read what it is up here.